All right, so basically, in this particular problem, we're given 1 pound of methane. And was it 1 pound? No, 4.3 pounds? 4.2 pounds. 4.2 pounds of methane and 50.0 pounds of air. Is that right? All right, this is like, okay, you go to the pantry, you go to the refrigerator, and you see, okay, I have, 1 box of pancake mix and, 5 eggs or something like that. And then you think, okay, well, how many pancakes can I make with the ingredients that I have? And so this is how much CO2 can you make with the ingredients that you have? Well, it depends. Each ingredient can make a certain number of pancakes based on the balanced chemical equation. The balanced chemical equation tells us that for every mole of methane, we'll need 2 moles of oxygen. We're going to get 2 moles of CO2 and 2 moles of water. CO2 gas. And so do we have just the right amount of each ingredient? Maybe not, When you go to your pantry or your refrigerator, do you have just the right amount of each ingredient? None of it's wasted, or you don't run out. So typically we run out of things, and what we run out of is called the limiting reagent, because what we run out of is what's going to limit how many pancakes you can make, or it's going to limit how much product we can make. And so the situation here is this. If we have just the right amount of both of these, we call it stoichiometric. And so it just turns out there's no waste. But more likely than not, when you go to the chemical shelf, reagent shelf, you're going to have too much of one and not enough of the other. And so we're going to determine which one we run out of. Can you look at this and tell me which one you run out of? Now, I know some people already got the answer on this one, but they did it in a way where, for example, they figured out if you have this much air, how much methane can you burn? That's one way that somebody did it. Another way somebody could have done it is if you have this much methane, how much air do you need? And do you have enough? So if we have this much methane, we can calculate how much air we need by figuring out, well, we need 2 moles of O2 for every mole of methane. From the O2, we can figure out how much air. That method is called comparison of moles. Comparison of moles is fine, but I do it a different method. I like the smaller amount method. Which ingredient would yield a smaller amount of product? That's the ingredient you're going to run out of first. And so the smaller amount method goes like this. Of course, you can use any method you want, and both methods are described in the book, but I'm going to skip the comparison of moles method and just go straight to the smaller amount. So, assuming we have plenty of air, how much CO2 can I get from 4.2 pounds of methane? And so what I do is I do yield from methane first. With this much methane on hand, I should be able to form how much CO2. And so I go 4.2 pounds of methane, CH4, and then we want to go to grams. So the conversion factor here is 453.6 grams per pound. And so that gives us grams of methane. From grams of methane, we know the molar mass of methane. A mole of methane molecules weighs 16.05 grams. And so we are now at moles of methane. So now we're in the heart of the stoichiometry mountain. So in other words, we just did kind of a gram to mole conversion here. But we had to do an extra step. We had to do a pound to gram and then a gram to mole conversion. Once we're at moles, now we can do a mole to mole conversion. The mole to mole conversion is this. I have 2 moles of O2 for every 1 mole of methane. And so now I have moles of O2, but moles of O2 is not moles of air. And so the next conversion will be a mole to mole conversion using the mole percent. The mole percent is that 100 moles of air contains 20 moles of O2. And so this is my 20%, I just flipped it. I flipped it because I want the moles of O2 to cancel. But it's still valid, 100 moles of air contains 20 moles of O2. And then I know how much 1 mole of air weighs. We calculated last time. 1 mole of air weighs how many grams? Yeah, 28.8 grams of air if I have a mole of air molecules. Okay, and then I want to go from grams to pounds. And so here, 453.6 grams in a pound. And so this tells me how many pounds of CO2 I can make. So, like in the kitchen, let's say I have enough. In the kitchen, I have enough methane to make, let's see, let's calculate it. It's going to be 4.2. Okay, times 453 divided by 453 cancels. So just go on to the next one. Divided by 16.05 times 2 times 100 divided by 20 times 28.8. And I get 75.36 pounds. 75.3. I'm only allowed 2 sig figs because of the percentage here. So we'll just go 75.3 pounds of CO2, or 75 pounds of CO2. So that much methane should be able to make 75 pounds of CO2, assuming I have enough air. I need the other ingredient because both ingredients are required for reactions. And so rather than determining how much O2 I have, I'm going to say, well, how much CO2 can I form from 50 pounds of air? And so what I'm doing is I'm looking at the CO2 yield from methane, and then I'll do the same thing to get the CO2 yield from air. That is, how much CO2 I can make from that much air. And so this is, again, conventional analysis here. I'll take 50 pounds of air and then convert it to what? I'll go from pounds of air to grams of air. Sounds right. 453.6 grams per pound. And so now I have grams of air. And then I'm going to go from grams of air to moles of air. And I know a mole of air weighs 28.8 grams to 2 sig figs. I'm carrying an extra sig fig, extra digit, not sig fig, extra digit here to minimize round off error. And so I have grams of air converted to moles of air. And then where? From moles of air to moles of oxygen. Here I know that there are 20 moles of oxygen for every 100 moles of air. It's 20% by mole. So now I have moles of oxygen. And then from moles of oxygen, I'm going to go to, not moles of methane, I'm going to go to moles of carbon dioxide, CO2. So the ratio here is that I'm going to get, what was the ratio? 1 to 1? Or 1 to 2. 1 mole of carbon dioxide is formed when was it 1? Or 2 to 2? 2 to 2? 2 to 2? 2 moles of CO2. 1 to 2? 1 mole of CO2 for every 2 moles of oxygen. Okay. That takes me to moles of CO2. From moles of CO2, I'm going to go to what's the molar mass of CO2? Yeah, that's 4401 grams of CO2 per mole. So now I have grams of CO2. From grams of CO2, I'll just go to pounds of CO2. So for every pound, we have 453.6 grams. And so that gives me pounds of CO2. And so let's go ahead and calculate this one. This is going to be 50, or times 453 divided by 453 is just 1. So divided by 28.8 times 20 divided by 100 divided by 2 times 4401. Oh, I already took care of that. Equals 7.64 pounds. All right, so as far as ingredients go, I have enough methane to make 75 pounds of CO2. And I have enough air to make 7.5 pounds of CO2. So what is the total amount of CO2 I can make? Would it be 82.6 pounds? Or would it be this one or this one? This one? Yeah, that's correct. And so I don't know why a lot of people do this. A lot of people add these two numbers together, but it doesn't make sense because let's say you have enough eggs to make 50 pancakes, but you have enough mix to make 100 pancakes. So a lot of people go, well, 100 pancakes plus 50 pancakes is 150 pancakes, but it's impossible. Here, so anyway, this is what's going to happen. We don't have enough air, and so we're going to run out of air, and we have too much methane. We don't have enough air for this methane, so we got to let some more air into the room or whatever to burn the rest of the methane. Okay, not everything in the air reacts. Only the O2. The nitrogen is what we call an inert ingredient. So just the O2 in the air reacts. All right, and so in theory, we can only make this much. And so this is what we call the smaller amount. And that's the yield. Okay, this we call the theoretical yield. The theoretical yield. This one would be impossible yield here. So we don't have enough one ingredient. And so the theoretical yield, the way I define the theoretical yield is it's the yield based on the what we call the limiting reagent. Yield based on the limiting reagent. The limiting reagent, limiting because it limits the amount of product we can form. Because we're going to run out. If we run out, then the reaction is going to stop. And if it stops, then we're no longer going to produce anymore. So once we form 7.6 pounds, it's done. We're going to have a lot of leftover CO2. How much leftover CO2 are we going to have? All right, so air, 50 pounds of air, this is what we call the limiting reagent. Reagent is just a reactant. 4.2 pounds of methane, this is what we call the excess reagent. The limiting reagent often is abbreviated LR for limiting reagent. Excess reagent, people don't normally abbreviate that with ER or anything like that. And so how much is left over? How much methane is left over unreacted? Okay, that's going to be our next calculation right up here. And so a common question that comes up is how much excess reagent remains unreacted? That is, how much leftover methane do we have? And the excess reagent remaining, let's say excess remaining is equal to the initial amount minus the amount consumed by the LR, limiting reagent. The initial amount is given. This one we have to calculate using stoichiometry. So the initial amount is 50.0 pounds of air. And so how much air was consumed by the limiting reagent? Well, that's just going to be a stoichiometry problem based on the limiting reagent. The limiting reagent was 4.2 pounds. Oh no, limiting reagent. Yeah, 4.2 pounds. Was that? Or was it air? I can't remember. Was it methane or maybe I got it mixed up. What one was the limiting reagent? Was it the air or was it the? It was the air. I have this wrong then. How much air is going to be left over? How much limiting reagent? Zero. There's nothing left over. We used all of it. And so the amount of limiting reagent that's left over is zero. Always. And so the excess reagent here is the 4.2 pounds of methane. Now this one we're going to have some unused portion of this. And how much unused portion depends on, how much 50.0 pounds of air requires to react with. And so we have 50.0 pounds of air, and then we're going to figure out how much methane we need for this. So what we're going to do is we're going to go from pounds of air to grams of air. And then from grams of air, we'll go to moles of air. So a mole of air weighs 28.8 grams. So molar mass flipped over. That takes grams of air out, and that gives us moles of air. From moles of air, we'll go to, well, where can we go? We can only go one place with moles of air. That would be where?
Is it amount consumed by the ZLR?
LR, limiting reagent. And so how much, well, we used up all the air, so how much methane did this air react with being consumed? And so we're going to go from moles of air to moles of O2. 20%, 20 out of 100. And then from moles of O2 to moles of methane. So what's the mole ratio between O2 and methane? So it's 1 mole of methane for every 2 moles of O2. And So now we did our mole to mole conversion. Now we're going to go to mole to gram conversion. So this is going to be 16.05 grams of methane per mole of methane. And then we'll go from grams to pounds. 1 pound is equivalent to 453.6 grams. Okay, and then that takes us to pounds of methane. So this is the number, what I'm calculating here is the number of pounds of methane that will react with 50 pounds of air. So let's just do what's in the parentheses here first. So it's going to be 50, all right, times 453 divided by 453 is just 1, divided by 28.8, times 20, divided by 100, divided by 2 times 16.05. And it comes out to 4.2 pounds of methane that we started off with, minus 2.7 2.78 pounds of methane consumed. Okay, minus 4.2, which means I'm going to have 1.41 pounds of methane left over. And so 1.4 pounds of methane left over. That's what we get. All right, any questions on this? It'll be a limiting reactant problem. So, like I said, there are two common ways to solve limiting reactant problem. One method is called the comparison of mole method. So the comparison of mole method works like this. You just see how many moles you start off with. And so moles is start. If I have 3 moles of carbon and 2 moles of O2, that's the comparison of moles. What I'm doing is I'm comparing it to the ratio that's required. For this particular reaction, a 1-to-1 ratio is required. So for every carbon, I need 1 O2 to form CO2. This is the reaction of carbon plus O2. Well, when I look at the number of moles, I need a 1-to-1 ratio, but I don't have that. I have three carbons and 2 O2s, which means I'm going to run out of one first. Which one am I going to run out of? I'm going to run out of the O2 because if I have 3 carbons, I need 3 O2s. If I have 2 O2s, I need 2 carbons. And so by comparing the moles here, we see that the excess reagent is going to be carbon here, and we're going to have some left over. How much are we going to have left over? 1. Because we started off with 3, 2 are consumed by the LR, the O2, and that leaves us with 1. The amount of limiting reagent left over is always 0. Now the limiting reagent is going to limit how much product we form. So the amount of product we form is 2. Because 3 carbons can actually form 3 CO2s, 2 oxygens can form 2 CO2s. And we'll pick the smaller amount, 2. We can't use mass. You know, comparison of mass doesn't work because these things weigh different amounts. So we need to do comparison of moles. Doing comparison of moles, here, you take a look. We need 2 antimonies for every 3 iodines. If we look at the moles at the start, we have 1 antimony and 1.5 iodines. Well, is that right? Actually, that's pretty close. This is pretty close to stoichiometric. Because it's, you know, if let's say, if we think in terms of 1/2, 2 times 1/2 is 1. 3 times 1/2 is 1.5. And so it's pretty close. But you can see that we have a slight excess of what? If I have 3 parts of iodine, so 3 parts would be 1.5, so each part would be 0.5. And then I need 2 parts of that. 2 times 0.5 is 1. And so I have a little bit extra antimony. I only need 1. I don't need 1.06. Do you see that? A slight excess of antimony. That's comparison of moles. I wouldn't have solved it like that. Although, you know, it's just preference. I would have solved it like this. I would have done the smaller amount method. The smaller amount method is we calculate the yield, or the amount of product that can be formed by the initial amounts of each ingredient, each reactant. And then we figure out which one is going to limit it, that is, which one is going to run out first. Okay, there's some additional calculations here. The reactant that yields the smaller amount of product is the limiting reactant. The smaller amount of product is the amount that will be formed when all of the limiting reactant is used up. We call this the theoretical yield. The theoretical yield is, you know, how much you can form based on the limiting reactant. In theory, that's as much as you're going to get. Okay, these are bonus calculations here. Calculate the amount of excess reactant that is left over. Which we did. There's a lot of writing on this one. And so here's another example of doing that problem earlier by the smaller amount. And so the first thing I do is, okay, I need both these ingredients. I need the antimony and I need the iodine. This is a reaction between antimony and iodine to form SBI3. And so one ingredient, well, how much SBI3 can I form from this ingredient? And then the other ingredient, how much SBI3 can I form from this? Figure out which one's smaller. And so the first ingredient we'll look at, 129 grams of SB, antimony. And so the plan is just to do this, stoichiometry, gram to mole, then a mole to mole, and the mole to gram. This will tell me how many grams of SBI3 I can form from that. How many grams of SB. We need the molar mass. This one we get off the periodic table, the antimony. We need the balanced chemical equation. We also need the molar mass of SBI3. Here's the balanced chemical equation. 2 SBs plus 3 I2s yields 2 SBI3s. Here's the mole ratio. Here's the molar mass of SBI3. Well, anyway, we just string it along. And so we'll do gram to mole to mole, mole to gram version here. We end up with 532 grams. Okay, with this particular ingredient, we can make 532 grams of product. What about the other ingredient? How much product can I make from the other ingredient? Well, the other ingredient is I2. And so we're just going to ignore this previous calculation. This is a whole new calculation. We're going to assume we have plenty of other ingredients. So what is the maximum yield of product from this? 381 grams of I2, ignoring what we just calculated for SB. And so we're going to go from grams of I2, this should be lowercase, grams of I2 to moles of I2, moles of I2 to moles of SBI3, moles of SBI3 to grams of SB. So just a gram to mole, grams of A, moles of A, moles of A to moles of B, moles of B to grams of B. So the molar masses. here's the setup. So grams to moles of A, moles of A to moles of B, moles of B to grams of B. 503 grams. So the iodine is capable of making up to 503 grams. The antimony is capable of making 381 grams. So how many grams am I going to make? Should I do 381 plus 503? No. Which one is it? Is it going to be 381? Or is it going to be 503? How many grams of SBI3 am I going to make? This is it. Maybe you go to your kitchen pantry and you look, oh, I have ingredient A. Ingredient A, I have enough ingredient A to make 381 cookies. But I need ingredient B also. And so you look in your pantry, there's ingredient B. Well, ingredient B, I have enough ingredient B to make 503 cookies. So ingredient A, I have enough to make 381. Ingredient B, I have enough to make 503. So therefore, I'm going to make 800. Over 800, close to 900 cookies, right? No, because you need both ingredients, right? And so how many cookies are you going to make? 381 or 503?
Take the difference between the two.
Would you take the difference between the two? That is 503 minus 381?
What's the excess? What's the excess? Initial amount minus the amount consumed.
Oh, okay, that's how much excess remains. How much left over. Okay, so it turns out ingredient A, once we make 381, we have no more ingredient A. Because we're going to use up all 129 grams of it. If we use all that's all we have in the pantry, 129 grams of ingredient A, we make 381 grams.
Isn't the result 532?
Oops, is that right? 532. 532. I was reading the wrong number, sorry. Now I've got to switch my thinking. Sorry, ingredient A here can make 532. And so you go to the pantry, ingredient A, you have enough to make 532, but we need ingredient B. So ingredient B, what was ingredient B again? Let's take a look. Ingredient B was the iodine. And so here's my ingredient B, and I see, oh, I got lots of ingredient B. Ingredient B, I have enough to make 503. And so how many cookies am I going to make? 503? Yeah, 503. Because this is what's going to happen. I'll make 503, and I'm going to completely consume all of my ingredient B. But I'll have some ingredient A left over here. And so I have too much antimony, not enough iodine. Well, how much of ingredient B am I going to have left over? So what we call this is this. We don't call 532 anything. We call 129 grams of antimony the excess reagent or the limiting reagent? Excess reagent. Okay, and this 503 grams of antimony triiodide, these are cookies. This would be called the well, 381 grams of iodine is the limiting reagent. This is the limiting reagent. The limiting reagent gives us the yield. This yield is called the theoretical yield. In theory, this is as much as I can make. I can't make 500 and whatever it was earlier because I don't have enough ingredients to make them. And so I got a theoretical yield of 530 grams of antimony triiodide. My limiting reagent is 381 grams of iodine. My excess reagent is 129 grams of antimony, which can produce this many cookies if I had enough iodine, but I don't.
So you minus 30 grams of this I3.
Okay. So let's figure out how many grams. And so this is the way I think about it. This is the smaller amount method. The limiting reactant is iodine. It produces a smaller amount. 129 grams of antimony is enough to produce 532 grams, but there's only enough iodine to produce 503 grams.
So you're short by
We're short on iodine.
29. Yes.
No, that's a little bit trickier than that.
Oh.
And so what we want to do is we want to figure out how much excess reagent is left over. In order to figure out how much excess reagent is left over, what's the equation for that? The excess reagent left over is equal to the initial amount minus the amount consumed by the limiting reagent, which is a new stoichiometry problem. And so this PowerPoint jumps straight into the amount consumed by the limiting reagent. What was the limiting reagent? Iodine, 381 grams. And so in this calculation, they're going to calculate the amount of antimony consumed by the limiting reagent. And so this is what they're doing here. They're given this is the limiting reagent. They want to figure out how many grams of antimony this amount of limiting reagent is going to consume. And so it's a new stoichiometry problem. So we calculate the stoichiometry here. It's going to be grams of iodine, to moles of iodine, moles of iodine, to moles of antimony, grams of antimony. And that'll give us the amount that's consumed. So let's take a look at that here. So we go from grams of iodine to moles of iodine, moles of iodine to moles of antimony. This is a typo here. From moles of antimony to grams of antimony. And so that amount of iodine will react with 122 grams of antimony. And so 122 grams of antimony were consumed. And so here's the equation here. I started off with 129 grams minus the amount consumed or used, and I have 7 grams of antimony left over. So that's a standard, what we call limiting reagent problem. Okay, I jumped ahead here in the presentation. I skipped the one section. Let me go back to that section now. I skipped this. I skipped this because I wanted to talk about limiting reagents first, and excess reagents, theoretical yield. There's actually more yields. You know, there's something called ideal yield, actual yield, percentage yield. And so the theoretical yield is the yield that's based on the limiting reagent. That's the amount that you can actually get. The other, you know, you can't. It's an impossible yield. And so we have the ideal yield. The ideal yield is the amount of product formed from the complete conversion of the given amount reacted to product, calculated based on stoichiometric principles. What is that? You know what that is? That's the theoretical yield. And so I define it differently. I don't even use ideal yield. Ideal yield is too ambiguous, the wording. In fact, nobody uses the ideal yield except Krakowicz. Everybody uses theoretical yield. And so this ideal yield is supposed to be the theoretical yield, and the theoretical yield is very simply defined. It's the amount or of product, or the yield of product from the limiting reagent.
Would it still be the denominator? If it's theoretical yield, would it still be in the denominator as the ideal yield is? According to the formula, it's the percent yield equals.
Oh no,
yield
this is
over-
different.
The denominator changes?
Yeah, no. We'll get to this in just a moment. The theoretical yield, in theory, this is how much you should get based on the stoichiometry. This is the theoretical yield. In theory, you should get that. But what happens is sometimes people don't get it. It depends. Like, for example, if you're making cookies, did you scrape every little piece of dough or out of the mixing bowl? And the same thing in chemistry. Sometimes it's not worth it, to scrape every little piece of precipitate out of the test tube. Might take you so much time, it's not even worth it. So you just say, okay, I'm going to lose a little bit. I'm okay with that. Do you want to spend, 15 minutes, 30 minutes, 45 minutes, an hour, scraping every little piece of precipitate out of there, not missing a speck? That's not worth it. It's a waste of time. And so what we're going to do is we're going to sacrifice a little bit of our yield. And so sometimes that's what happens. Sometimes what happens is I don't want to scrape it, every last bit of cookie dough out of there. I'll just leave some because it's too much time. And so your actual yield is the amount you actually get. And this varies depending on the person. Some people are more particular about these. Some people are more have more patience, etc. And so it depends. And so in theory, we should have gotten, let's say, 30 cookies. But sometimes it doesn't matter. Sometimes they break. Sometimes other things happen. You drop some, etc. So the actual yield can be less than your theoretical yield. This is something we want to keep track of. And so this is the measured quantity determined by experiment or experience. It's lower than the theoretical yield as a result of losses. And there are reasons for losses. Some of the reasons are you just don't want to waste the time getting every little speck out of there. Others are out of your control. Like, for example, incomplete reactions are out of your control, or impure reactants are out of your control, or side reactions are out of your control. Some things are in your control, and it's a compromise. Other things are just by accident. You accidentally lost some. That's it. And so we have something called the percentage yield. The percentage yield tells us, well, how close to the theoretical did you get? You're supposed to get, let's say you're supposed to get 100 cookies, you got 99. You got 99% yield. And so the percent yield is the actual yield, what you actually got in the experiment, versus theoretical yield, what the calculations told you you're supposed to get, or what you should have gotten in theory, times 100%. So let's look at an example of this here. A solution containing 3.18 grams of barium chloride is added to a second solution containing excess sodium sulfate. Here, I already know what the limiting reagent is. Do you know which one's the limiting reagent? Is it the barium chloride or the sodium sulfate? I know what the limiting reagent is, even though they didn't even tell me. How? Because they told me what the excess reagent is. If that's the excess, then the other one must be the limiting. Because it turns out that limiting reagent is very important in chemistry, because nobody wants to spend the hours and hours and hours to get everything perfectly stoichiometric, right? Everybody's going to say, okay, which one? Like if you have a recipe, for example, let's say actually, did I bring my book? I forgot my book. One of the problems in the book is this. You know, you're making pastries, and you need some baking soda, and you need some citric acid. And the baking soda and citric acid react. And so if you have a pastry, which one would you rather have a slight excess of? Would you rather have a slight excess of citric acid, or would you rather have a slight excess of baking soda? And so you might ask yourself, you know, which one tastes better, citric acid or baking soda? Have you tasted baking soda, just straight? It tastes like what, pulverized rock or something like that, a little bit? And you know what citric acid tastes like? Citric acid tastes like lemons, because lemons are 80% citric acid. And so which one do you think you'd rather have more of? Like the pulverized rock or the lemon, the sour lemon taste? Well, it's a personal taste preference, but it's one of those things that chemists would think of, you know, what would be a better excess reagent, because I'm not going to waste a lot of time. I'm just going to go ahead and go, okay, I'll put in a little bit extra of this, you know. So I make sure I can completely consume the limiting reagent. Well, that's the case here. They wanted to make sure they completely consumed all the barium chloride. They didn't want any barium chloride left over, so they added a little bit extra sodium sulfate. They could have tried to do this stoichiometrically, but it's impossible, you know, to get it to the nearest atom or molecule at the particulate level. So, anyway, let's take a look at this problem here. 3.18 grams of barium chloride is added to a second solution containing excess sodium sulfate. Barium sulfate precipitates. I wouldn't have, you know, on the test, I wouldn't have given this. I would have been expecting you to tell me what happens when these two are mixed. Our book is just telling us what happens. If the actual yield is 3.37 grams, calculate the percentage yield. All right, so barium chloride, what's the formula for barium chloride? BaCl2. Sodium sulfate? Na2SO4. What kind of reaction does this look like? Yeah, double replacement. And so the products? Does that look right? Yeah, this is not Na2Cl2. This is just NaCl. We don't worry about balancing yet. We just want to make sure we get the formulas right. We'll balance it later. But we'll balance it if there's a driving force. So sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. Well, barium sulfate, that's not soluble, so it's going to precipitate a solid. Sodium salts are all soluble, so that's aqueous. So aqueous, solid, aqueous. So we have driving force, we get precipitation. Now, they told us that this is the excess, this is the limiting reagent here. And we're going to calculate the theoretical yield of barium sulfate based on the, what, excess reagent or the limiting reagent? Based on the limiting reagent. This saves us doing an extra stoichiometry calculation, because if they didn't tell us which one was limiting and which one was excess, I'd have to do a stoichiometry calculation based on ingredient A and based on ingredient B. If I have more ingredients, then I got to do one based on each ingredient present. You know, we got like 10 reactants. We're going to do 10 stoichiometry problems. But since they told us this is the LR, then we know that the theoretical yield is based on this. So we've got 3.18 grams of barium chloride, and then where do I go? I'm going to go to Moles. Yeah. And so barium is 137.33. And the two chlorines, each one's 35.45, so 2 times that is 70.90. I get 108.23. And so a mole of barium chloride formula units weighs 108.23 grams. So the grams of barium chloride cancel out. So now I'm at the heart of the stoichiometry map. So I got moles of A, now I want to go to moles of B. Which one should I choose as B? So moles of A to moles of B, which one should I choose for B? Barium sulfate. Well, it turns out it's a 1-to-1 mole ratio, so I have 1 mole of barium sulfate for every 1 mole of barium chloride that reacts. So this is how many moles of barium sulfate precipitate should be produced by my limiting reagent. But I don't want moles, I want grams. And so I need to figure out the molar mass of barium sulfate. So barium is 137.33. Sulfur is 32.07. 4 oxygens. Each oxygen is 16. 2 oxygens is 32. 4 oxygens will be 64.00. That's 10. That's 40. 233.40. 233.40 grams of barium sulfate per mole. So everything cancels out and gives me grams of barium sulfate. So let's just calculate the number here. So just do that here. 3.18 divided by 108.23. Times 233.4, 6.85. Hmm. 6.857. I'm allowed 3 sig figs. Did I make a mistake? I got a different number this morning. Let's see. Oh, I see. I made a mistake. Do you see my mistake? This is not 108. It should be 208. So let me recalculate that. Sorry. 3.18 divided by 208.23 times 233.4. 3.56. 3.564. This is the same answer I got this morning. Okay, 3.564 grams. What do we call that? That's the yield based on the limiting reagent. The yield based on the limiting reagent is called the theoretical yield. And so this is my theoretical yield. So the percent yield is this. Percent yield is the actual yield, which is 3.37. They lost a little bit, right? They lost a little bit of the precipitate. How do they lose a little bit of the precipitate? It's easy. You know, do you want to scrape all that precipitate out of the test tube? No, it's a hassle. So maybe they'll lose a little bit. Maybe that's quite a bit of loss, but I don't know. Over 3.564 grams times 100%. So let's see what we get. 3.37 was how much they actually got, divided by 3.564, which is how much they should have gotten. It was out to 94.55%. 94.55% yield equals a 94.6% yield. 94. And so that means they lost 5.4% of it. That's kind of a big loss. They got a different number than me. They got 94.7. Why? Do you see why they got? Yeah, they did an intermediate round off here. The intermediate round off here is this is 3.564. I carried extra digits there. They might also, the molar masses, yeah, they rounded this molar mass. 208.2, I used 208.23. And so their answer is slightly different than mine due to round off error. All right, let's take a look at this next problem here. Any questions with this one? Well, actually, it's break time, so let's go ahead and take a break, and then we'll start this next problem.